Hello everyone. Today I will be discussing some of the work that I have been doing for my master's thesis on modeling the influence of small-scale topography on surficial temperatures at the LCROSS impact site. Let's begin with some background. Unlike Earth, the Moon has a very low obliquity, with its rotational axis inclined just about 1.5 degrees relative to the plane of the ecliptic. This means that near the poles, the Sun never wanders far from the zero elevation horizon. If local topographic features create a horizon that is more than a few degrees above zero elevation in all directions, then the Sun will never rise. This condition is most easily satisfied within impact craters, which is why many of the Moon's large polar craters are home to permanently shadowed regions, or PSRs. PSRs are of scientific interest because, in the absence of direct solar illumination, they can maintain extremely low temperatures over geologically long timescales, an effect that is further enhanced by the fact that the Moon has no atmosphere to transfer heat between the illuminated and shadowed portions of its surface. PSR temperatures can be sufficiently cold to trap volatile materials like water that would otherwise rapidly sublimate away, allowing them to accumulate on the surface and in the first few meters of the subsurface. These deposits could be extracted and used to support long-term missions, like those currently being planned for humanity's return to the Moon this decade. However, there is still significant uncertainty regarding the exact distribution and abundance of lunar volatiles. Orbital surveys using neutron spectroscopy, reflectance measurements, and direct imaging have generally produced inconclusive and often inconsistent results. Given the strong dependence of volatile stability on temperature, perhaps the most powerful tool at our disposal when assessing where volatiles might be stable are the temperature maps produced by the Diviner Lunar Radiometer on board the Lunar Reconnaissance Orbiter. Unfortunately, these maps are limited by the resolution of 240 meters per pixel. While sufficient for examining global trends, each diviner pixel necessarily averages over variability at small scales that might significantly affect the available cold trapping area. Here's a figure that I like to use to illustrate this problem in a context that is more easily relatable. On the left is a digital elevation model of the York University campus and surrounding area, produced by the Government of Ontario at a resolution of half a meter per pixel. On the right is the same dataset, downsampled to match the resolution of the diviner data. As you can see, while the general shape of the terrain is preserved in the downsampled data, any attempts to model illumination conditions on campus would not go particularly well if all you had to work with was the data on the right. Although the Moon doesn't have any dramatic topographic features like buildings on its surface, it's not difficult to imagine that the low resolution data that we have are missing a lot of important information at small scales. Hayden et al. 2021 highlight the importance of the resolution problem by modeling micro cold traps, or areas outside of the large PSRs where small-scale surface roughness creates cold traps on scales down to 10 centimeters on otherwise sunlit terrain. The diviner data do not capture features on this scale, which may expand the Moon's available cold trapping area by 10 to 20%. The goal of my project is to expand this work into the PSRs themselves by examining how small-scale surface roughness creates micro-ultra-cold traps that are protected from both direct and singly scattered sunlight, as well as thermal emission from illuminated terrain. Because singly scattered sunlight and thermal emission are the dominant energy sources within PSRs, these doubly shadowed regions would be much colder than the diviner data would otherwise suggest. You may recall from my title that I am focusing on the LCROSS impact site. This is because the LCROSS impact provided direct confirmation of the existence of lunar volatiles, meaning that we can attempt to link the observed abundances in the impact plume with our model temperatures. In effect, we are attempting to answer the question of whether or not the LCROSS results can be explained by the subpixel temperature distribution at the impact site. With that background information under our belt, we can move on to the work that I have been doing. The methods can be divided into 3 sections. First, we will have to generate the terrain that we will be working with. Next, we have to model the sunlight that is incident upon that terrain. And finally, we need to convert the incident solar flux into temperatures. To generate our terrain, we take the 240 meter per pixel digital elevation model created by the Lunar Orbiter Laser Altimeter and interpolate it to our desired resolution of 1 meter per pixel. On top of the interpolated data, we overlay an artificial Gaussian surface defined by a characteristic Hurst exponent and root mean square slope, whose values, shown here, are chosen to replicate those observed on the lunar surface. Next, we have to illuminate the surface. This is a purely geometric exercise, albeit a fairly involved one. The amount of light scattered by a terrain facet K towards another facet J is a function of 4 vectors, solar incident vector at k, the surface normals at k and j, and the vector between the two facets, as well as the angles between them. All of the vectors and angles are illustrated here in this figure. Because only the solar incident vector and the angle it makes with the surface are time-dependent, all of the other terms can be combined into a single value known as the view factor, whose definition is the first equation on this slide. Also on this slide are the other critical equations for the model, for the scattered light and thermal emission that are incident upon the PSR terrain facet. We illuminate the light scattering terrain by first locating the subsolar point using the DE 421 lunar ephemeris. From that, we derive the altitude and azimuth of the sun as observed from each terrain facet. These values are then compared to the location of the horizon, calculated using the methods of Mazarico et al. 2011 to determine the visible fraction of the solar disk, which is used to scale the solar constant. In addition to using the horizons method to determine solar visibility, we also use it to assess how the small-scale features of our upscaled terrain affect the visibility of the light scattering terrain. Rather than finding the true horizon, or the maximum elevation blocked in each direction, we instead find the maximum elevation blocked in the 2.5 by 2.5 kilometer region immediately surrounding our point of interest. This creates a local horizon that we can compare to the positions of the light scattering terrain points as seen in this figure. The thin red line is the local horizon. Purple points represent light scattering terrain facets that lie below the horizon and thus are blocked, while the white points are above the horizon and visible. To determine the magnitude of the thermal emission from the light scattering terrain, we need to know the surface temperature of each facet. In principle, we could apply a full thermal model, but for the sake of simplicity and computational time, we assume that the light scattering terrain facets are always in thermal equilibrium and only subject to direct solar illumination, so the temperature is defined using this simple equation. Of course, these assumptions break down when the sun is below the horizon, leading to an underestimation of temperatures in shadow, but this will have a minimal effect on our results, since we are most interested in the maximum temperatures. In the regime where the sun is above the horizon, this very simplified model agrees with diviner temperature measurements to within 5 to 10 Kelvin. We do not have the luxury of using a simple model on the PSR terrain, however. Here, we do have to use a full thermal model. When examining surface temperatures, members of our group have typically relied on the thermal model of LCROSS for 2021. I found that this model is not well adapted to the low illumination conditions within the PSR. The model of Martinez and Siegler 2021 seemed promising as it was specifically designed to deal with the low temperature regime. Unfortunately, it took an unacceptably long time to run given the large number of points it will need to be applied to. Because Martinez and Siegler have provided the input data that they used to validate their model, I was able to explore modifications to the two models to combine the efficiency of the LCROSS model with the accuracy of the Martinez model. I found that by adding the depth and temperature dependence of the thermophysical parameters, density, thermal conductivity, and heat capacity from the Martinez model to the LCROSS model, I was able to closely replicate the Martinez and Siegler results in a much shorter amount of time. A comparison between the different model results can be seen in this figure with the input data shown on the top panel. We can also validate our model results by comparing them to the diviner temperature measurements. Here, I plot the diviner temperatures of the pixel containing the LCROSS impact site as a function of subsolar longitude. If we overlay the results of our model at 240 meters per pixel, we can see that the model closely follows the diviner measurements, replicating both the magnitude of the temperature variations as well as the double-peaked shape. Even at low insolation, the difference between the modeled and measured temperatures is small, providing additional support to our simplified approach to modeling the thermal emission. Now we can move on to the results. This section is fairly short as I am still working on the analysis, but I welcome any thoughts that you might have. First, I'll mention the specific parameters that we used for our model. We simulate the illumination conditions over one draconic year with 3-hour time steps, beginning with the full moon on January 11, 2009. We choose 2009 because that is the year that the LCROSS impact occurred, and we simulate a draconic year because the illumination conditions at the end of that year will be approximately the same as at the beginning. This is important because we run the thermal model 5 times to allow the temperatures to equilibrate, using the final output of one run as an input to the next run. Ideally, we would simulate the entire 18.6-year lunar precessional cycle to eliminate the small variations that occur between draconic years, but those differences are relatively small and we see rapid convergence of the temperatures regardless. Here, I present the maximum temperature map of the LCROSS impact pixel at a resolution of 1 meter per pixel. Several things are immediately obvious. First, there is a fairly sizable range of temperatures from a minimum of 35 Kelvin to a maximum of 60 Kelvin, supporting the idea that small-scale terrain features create a wide range of thermal environments. Second, while the frequency of maximum temperatures is more or less normally distributed, as can be seen in the bottom figure, the spatial distribution of those temperatures is highly heterogeneous, with the coldest temperatures clustered around the right edge and the warmest near the bottom left corner. This means that we cannot assume that the potential volatile content of any particular pixel is roughly the same anywhere within it, highlighting the need for a better understanding of the physical characteristics of PSR terrain at these scales before sending a resource extraction mission. Now we can ask the question of whether or not the subpixel temperature distribution can explain the LCROSS volatile abundances. In short, no, it cannot. But this shouldn't be too surprising for several reasons. First, the abundances measured in the LCROSS impact plume don't decrease with increasing volatility. For example, H2S is almost 8 times as abundant as CO2 despite having a stability threshold that is lower by about 5 Kelvin. Additionally, NH3 and SO2 were measured at concentrations of 6% and 3% relative to H2O, despite all three having the same available cold trapping area. This supports orbital evidence that the Moon's volatile contents are strongly limited by delivery sources rather than the available cold trapping area. Additionally, we are modeling surficial temperatures, and the LCROSS impact was not a surficial event. It is estimated that the impact exhumed material at least 2 to 3 meters below the surface. As a result, some of the measured volatiles likely came from the subsurface, where abundances are not as strongly linked to temperature as they are at the surface. So, moving forward, there is a lot of work that can be done to expand on these results. First, we can look at other points in other PSRs, as the geometry of the light scattering terrain differs from crater to crater. We can also explore modifications to the terrain parameters by changing the RMS slope, Hurst parameter, and albedo. The terrain that we created was based on the average physical parameters of the lunar highlands, and it is possible that the highlands are not representative of PSR terrain. Finally, we can investigate the seasonality of temperatures, specifically how much time each pixel spends at its maximum temperature. This is important because a surface that spends a few hours each month at, say, 60 Kelvin will be much more hospitable to volatiles than one that sustains 60 Kelvin continually, even if the species' stability temperature is below 60 Kelvin. Although both will lose volatiles if the loss rate is greater than the deposition rate, the mean loss rate will be lower if the surface experiences occasional temperature spikes rather than sustained high temperatures. In summary, PSRs are likely to play an important role in the future of lunar exploration due to their ability to cold trap volatile molecules like water that can be used to support long-term crewed missions. However, our knowledge of the potential volatile distribution is constrained by the low-resolution orbital data that we have on hand. As a result, more detailed studies, either from orbit or in situ, are likely needed in advance of Artemis Base Camp site selection and our return to the Moon to stay. That is all that I have for you today. Thank you for your time, and I look forward to taking your questions.